Hi, I'm Dr. Gary LaMotte. I'll be presenting a talk for myself and Dr. Shane LARSON of Sierra Northwestern University. The talk is entitled Graviton Mass Constraint from LISA Compact Binary Catalogues. And I'll share this screen with you. Our goal is to determine the feasibility to use LISA to measure the speed of gravitational wave propagation by using a synthetic LISA catalog. Regarding motivations, measuring the speed of gravitational wave propagation provides a test of general relativity. General relativity predicts that gravitational waves move at the speed of light. Any measured difference in gravitational wave speed versus light speed would imply a non-zero graviton mass, and thus favor certain alternate theories of gravity. The approach that will be used will be to utilize visible white dwarf multi-messenger binaries. We will obtain a light curve from these binaries, which will give orbital phase information. LISA will provide gravitational wave information, and specifically the gravitational phase information. Now, I want you to imagine something. I want to have you imagine that you have a white dwarf binary somewhere out in space that you can see with both a telescope, as well as you will be able to receive gravitational wave signals from the white dwarf binary. The binary, the binary will be located on edge with respect to how we will see it from Earth and with LISA. And thus, the binary will undergo eclipsing as it moves through its orbit. So I want you to get a visual picture of that. And now we'll go ahead and proceed. Okay, here is our binary on the left side of the screen. Again, think of it as orbiting in a plane such that we see it edge on. Orbital phase information will be transferred from the binary to the Earth and to LISA by two methods that are physically determined. One is from an electromagnetic signal, as shown above. The signal will have a phase that depends on the orbital period of the binary. The binary will also generate gravitational wave signal that will also depend on the orbital phase of the binary. The binary that we'll specifically look at in a moment has an orbital period very short, and actually that of slightly less than 13 minutes. When the signal is received at the Earth, as shown on the right side of the diagram, the electromagnetic signal and the gravitational wave signal may or may not be in phase with each other. In the diagram, it shows that they're not in phase. And what this demonstrates, if they're not in phase, is that there must be a small mass that the graviton has, and thus general relativity would not be correct. On the other hand, if the phases arrive together and the phase is congruent one with another, then we will see that the signals are traveling at an equal speed. Now, I want to be more specific with this and show you an additional slide that would be the signal as we receive it at Earth and at LISA. So this is not the emitted signal, but this is the signal we would receive in our data collection. And this is an idealized curve. This curve shows both the light curve and the gravitational wave curve for the white dwarf binary known as J0651, which again has an orbital period of slightly less than 13 minutes. I want to orient you to this plot. On the x-axis, it is time as given in seconds. On the left-sided y-axis, what we're seeing is the light curve intensity for the binary. That's in blue. And you will see that there's a low point in the light intensity just to the right of the mid portion of the slide. That's where the maximal eclipse takes place. Now, on the right y-axis, that's the gravitational wave strain amplitude, and that's in green. And if we have an optimally oriented detector, and if the binary is seen edge on, as I've described above, then we will get a sinusoidal wave as the gravitational strain amplitude. And again, that's shown in green. If there's a phase difference, as I've shown in the diagram, then the light curve and the gravitational wave curve will be slightly out of phase, as given by the arrow at the mid part of the screen. That would indicate a non-zero graviton mass. If, on the other hand, the phase difference is 0, this indicates a graviton mass, actually a rest mass of 0, and is consistent with general relativity. Okay, now I want to move from discussing a single binary, as we just looked at in the last two slides, to discussing an entire group of white dwarf binaries. In order to do this, since we don't have any actual data from LISA, we are utilizing LISA catalogues. We will be using a program that's been developed at Northwestern called COSMIC. And COSMIC is a population synthesis code that will produce simulated Milky Way binaries. This will be a very large catalog. We will need a subset of this catalog. So what will be done next is to select, to select a smaller catalog that contains only binaries of interest to LISA that have sufficient signal to noise and other characteristics. From that catalog, we will select a smaller subset, and those will be binaries that we can identify as multi-messenger binaries that we will be able to obtain electromagnetic signal and information, as well as gravitational wave signal and information. With those multi-messenger binaries, measurements will need to be made. These simulated binaries are going to be used to model gravitational waves and electromagnetic observations. From these simulated binaries, we will calculate the uncertainties to model the accuracies of the phase measurements of both gravitational waves and electromagnetic waves. The phase uncertainties that we calculate are used to constrain the mass of the graviton. So, in summary, LISA will provide a means to measure the speed of gravitational wave propagation independent of other measurement methods. This will be done using white dwarf multi-messenger binaries. This will be accomplished by measuring phase differences of light curves versus gravitational wave strain curves. Measurement uncertainties will be determined by using simulated catalogues of white dwarf binaries, as I just described. Phase difference measurements with associated uncertainties test GR, general relativity, and constrain the graviton mass. Lastly, I'd like to give a personal note. This is such exciting work. I am so proud and honored to work for and support the LISA project. Thank you very much for your attention.